Okay, can you see the board now? Is it clear?
Yes, sir.
Yes, sir.
Okay, thank you very much. So today's topic of continuous uh, distributions in case of internet traffic. So we have studied till now we have studied binomial, geometric, Poissons. So these were the discrete distributions, and now it's time to study continuous distribution, normally used to model inter what we call it inter-arrival time data, I8 inter-arrival time data between packets, between flows, between session, and also the session size. Session size is a discrete variable. It's not a continuous variable, but session duration is a continuous variable. So let's start with some basic cases in which the number one, the basic distribution is uniform distribution. The uniform distribution, and I will use the notation by your book that if a random variable is x, okay, so it is said to be uniformly distributed in the domain. It has a domain minimum value a and b, okay, and I mean all of the values between a and b are equally likely. That's why like if we plot the probability function, so if this is a, if this is b, so all of the probabilities are equally likely. That's why we call it rectangular or uniform distribution. And its probability density function is very simple. It's equals to 1 upon the difference b minus a. This is the this is the and this is the probability between lying here and there. And obviously the probability in this region less than a is 0, and probability of any random variable x assuming values greater than b is also 0. So in this region the probabilities of that random variable, this is x here, x, it is 0 because it is never occurring. And in this, and what is the probability between this region? So this is governed by this density function. So this is the basic density function, the one of the most simplest uniform continuous distribution. And you should know the expected value is e of x, you can easily derive it, is equals to uh, a plus b divided by 2. This is the mean value of this random variable. So any numerical in which you ask this, to expected value is just minimum value plus maximum value divided by 2. So this is, just note it down. So this is the uniform distribution. Now we come to in case of internet traffic, we haven't seen any significant example which is following this particular distribution. But now I come to in the second case, I come to a very important distribution which is called as Gaussian or normal distribution. This is quite commonly observed in case of internet traffic, and it is parameters by two parameters, mean value and variance. Mean is denoted by mu, and the variance is denoted by sigma square. So the density function is quite interesting. The density function of a random variable, uh, we denote x as a subscript. This is the random variable, this is the random variable, this is the value here, and it is equals to 1 over sigma 2 pi and then e to power minus 1 by 2 and x minus mu divided by sigma square. Just need to correct this is so this is the kind of called which we called it as a probability density function, and we write this as uh, n random variable x. We short write it as n mu comma sigma square. So this is the density function of a Gaussian or a normal distribution, and it has been quite commonly observed in case of internet traffic and many other distributions. And if you want to derive it, the formula can be very easily obtained. You can see in various books of statistics that if you have a binomial distribution, um, if you have a if you have a binomial distribution, we have studied the case of the binomial distribution. If we have a binomial distribution, in this case, if in this case, if n tends to probability of a single event is constant, then it tends to normal distribution. So this is just its theory, but the thing is that you should know where to apply which distribution. In case of Gaussian distribution or normal distribution, you can see that it's parameterized by the mean value and variance. And if you see the plot in your book, they have seen various plots if I plot the Gaussian, sorry, I have to show go up. So this is the plot of the Gaussian random variable. So it can be like this. It can be like this. It can be like this. You can see that in this case, all of these three different distributions, they are not different, but they are the same. The parameters are different. They have the same. This is the mean value. All of this data has the same mean value, and this thing controls the variance. So this is the standard deviation. In this case it is less, and now it is more standard deviation. Deviation, so it depends upon if the shape is like bell curve, so it means that your data behaves like a Gaussian distribution. In real life scenario, where to apply this kind of distribution, there's a very good hint in your book that I can read it out. Generally speaking, if you know the quantity is supposed to have a certain standard value, and you also know that there can be small variations in this value due to small independent random effects. So therefore, it is reasonable to model this random variable by using Gaussian distribution. For example, just to clarify that if there's a random variable x, so x can be any value. So uh, we are interested in what kind of distribution it follows. If we are sure that x is close to some fixed value mu, any value, but there is some kind of noise effect or noise impact or any random effect, that's very common in case of internet traffic or in case of many engineering applications. If there's any random effect or noise impact and the value is fixed, it's supposed to fix, then it means that you can safely model them by using Gaussian distribution. Normally, if you are aware of this distribution in your undergrad, that this distribution of error is commonly modeled by using Gaussian distribution. And let me tell you some important formulas regarding this distribution. You should note this because will have to do numericals regarding this. As you can see that the Gaussian distribution is symmetric about mean. Okay, and then is this is the negative asymptote minus infinity, and this is the plus asymptote, so it goes on the both sides. um, the sigma square parameter controls the width of the bell, and the larger this parameter, the wider the bell will be. Okay, so uh, um, let me write it down, that the probability that a Gaussian or normal random variable x, this is random variable x. Okay, it lies between their standard formulas, mu minus sigma and mu plus sigma, is about 68.26%. These are some universal facts about this. And same case, Gaussian random variable to lies between lies between mu minus 2 sigma and mu plus 2 sigma. Is is will it be greater or less?
I think greater.
Why? Because no, you are looking at more area, because previously you are looking at just a small part, and then you are looking at more larger part. Okay, so you are right. So because the domain is now bigger, so you are now more flexible, so obviously this will be greater, and it has been found to be 95.44%. And another notation you should note, that probability that a Gaussian random variable lies between mu minus 3 sigma and mu plus 3 sigma, obviously this will be more greater. This is 99.73%. So you should know so in this cases, the numericals can come both ways. Either you can be given this side, and you may be asked to do this, or you may be given this side and you might be fine to do this. So this is some universal facts, that if a Gaussian random variable, if a random variable x is Gaussian, then the probability that it will lie between mu minus sigma and mu plus sigma. Mu is the mean value and sigma is the standard deviation, then is 68.26%. um, if we increase the range, or standard, or the width of the bell curve, mu minus 2 sigma and mu plus 2 sigma, we are looking at more larger size, and then mu minus 3 sigma and mu plus 3 sigma, we are having a more larger size. So obviously the chance of random variable falling between these values will increase more and more. Okay, so there's an interesting example regarding the Gaussian distribution in let me write down the data here. uh, so let me so the example here is that it's just will use this. So the example problem is that, let me read it down and summarize the question here. The question is that, suppose that the number of packets that arrive on a link to a router in there is a router. Okay, so there's a link and there are packets coming inside the router. These are packets, they are coming this way. Okay, suppose that the number of packets that arrive on a link to a router in 1 second interval can be modeled by a normal distributions with parameters. So so the number of packets that arrive on a link to a router in 1 second interval. So during 1 second interval, they are saying that uh, the number of packets can be modeled by using a normal distribution with the parameter. So they are saying that the parameter, they say that n20 comma 4. Okay, so the mean value, this means that the mean value of the number of packets is 20, and uh, the standard deviation is you can see that what it's it is you need to note that this is, if you're giving this notation, so it means that mu comma sigma square, so it means that this value is not sigma, this value is sigma square, so sigma square is equals to 4, so this implies sigma is equals to 2. Okay, uh, how how many packets how many packets uh, we expect to see to see with 99% confidence. So this is the question. So very simple question. This is router R. The packets are coming, and you can see that we can use the continuous distribution here, which is used. It can also be used in discrete cases, because in this case you see that they are using in a discrete manner, because it is talking of because the 20 is the mean value of the number of packets in 1 second, and 4 is the mean value, is the variance of the number of packets in during 1 second interval. So they have defined 1 second in the entire experiment is based on a time second 1 second observation. Okay, so how many packet we expect to see with 99% confidence during this, uh, although that we know that the mean value is 20. Okay, and then and the variance is 4, and therefore this is the so how many packets we expect to see with 99% confidence. So obviously then we need to see the formula here. So coming back to this, so it's actually this, you can see that this is the case 1, this is case 2, and this is case 3. So this is the we have to reverse map in this case, because this is the case 3 in which um, uh, because 99% confidence is belongs to this region, mu minus 3 sigma and mu plus 3 sigma. So obviously if we are asked to do this, then obviously we have to reverse map this thing, that we are giving this value, that 99.73% is our confidence, then obviously the values will lie between mu minus 3 sigma and mu plus 3 sigma. So that's why we will do it here. So therefore the number of packets we expect to see with 99% confidence will be, it will be we will just reverse track this case 3, that will be mu minus 3 sigma and mu plus 3 sigma. So let's do it here. So this will be for 99% confidence or probability, the Gaussian random variable behaves like what we said. It is behaves like
Mu
mu
plus
minus what,
minus 3 sigma.
mm, and behaves like that should be more clear, behaves like in between. Okay, so this will be in between what, mu minus 3 sigma and mu plus 3 sigma. So mu is how much, 20 minus 3 into 2, sigma is 2, and 20 plus 3 into 2, so this is 20 minus 6, and this is 20 plus 6, this is 14, and this is uh, 26. So how should we state our answer? That that we expect minimum 14 and maximum 26 packets. Okay, that is if we were to measure packets arrival over a long period of time. um, okay, so this is the our expectation. So okay, is it clear? So the main thing is that you need to know these three cases, the formula for these three cases. So these are the main points you need to know this, because this is very important. And another two more distributions are important. Let me write down the formula here. Okay, the number third distribution is uh, the number third distribution is exponential distribution, and obviously this is a random variable x follows exponential distribution with this one parameter lambda. Okay, this is lambda, which is called as a rate parameter. So the density function is given by um, the density function of this exponential and a variable is given by lambda e की power minus lambda x. So this is the density function of and if you ask of the CCDF, so this is 1 minus e की power minus lambda x. Okay, so what is the CCDF? I think you all know this: probability that random variable x is less than equals to any given value is equals to, so this is just more elaborate, 1 minus e की power minus lambda x. So this is the exponential distribution. So I think we have already discussed about this distribution, and there is just a small numerical example just to illustrate the use case. The example is very simple. They say that they are just measuring telephone calls or Skype calls or WhatsApp calls. There are, so they say that an average length of a phone call is 3 minutes. Okay, and assume that the length of a call is exponential random variable. What is the probability that the call lost more than 6 minutes? Okay, so they say that the phone call phone call duration is modeled by a random variable x, and then they say x, the problem says that assume that the length of a call is exponential variable. We say that it is given that x follows uh, exponential distribution. Okay, and what is the probability that x is greater than 6 minutes? and and what they say that another thing is given that suppose that the measurement showed that average length of a phone call is 3 minutes. So we are given that the average length of phone call e of x is equals to 3 minutes. Okay, so obviously for lambda is because it is the exponential distribution is parameters by the lambda. So lambda is a rate parameter. So to solve this problem, we always need the lambda, the rate parameter. And obviously then to find the rate parameter, you will just inverse the mean value. Okay, so this is the rate parameter will be equals to 1 by 3. Okay, so what is the probability that the call lost more than 6 minutes? So if we use the formula here, so this is the formula. I can write it down here. I can just the the main formula, probability that x less than equals to x is equals to 1 minus e to power minus lambda x. So this formula is giving you the probability that a random variable capital X, which is exponential random variable, is less than some small value x, follows this. But here we are asking this. So how to do this? Can we use this formula like this and then do this? Like because you know that this is called as f f of x. This thing is called as density function. So what if I do this f of 6? What is f of 6? Or more clarity, or it will be like like x, f of x. So it will, I can write it down is that x is less than equals to 6 min. So if I do like this, so I can just like I can do like this, 1 minus e to power minus 1 by 3 and then x is 6. Okay, but we do not need this because this actually means the random variable, the call duration is less than 6 minutes. But what we want something more than 6 minutes. So anybody can help me here?
So area under the curve मालूम कर रहे हैं?
No, no, because you see that the main formula of all distributions just like this. This is called a this is called a CDF. CDF gives you the probability that a random variable x is less than any given value. So if you can see here, this small x is a given value and this capital X is a random variable. So it's so this is the distribution function. And so I'm just using this. So the question is very simple, but the thing is that this is giving you, the CDF gives you the probability that a random variable is less than any given value. So you can change x to 1, 2, 3, 4, 5, 6, whatever, but the answer you will get is about probability that the random variable capital X, which is going to be exponential here, is less than the your given value. Okay, because you are giving your value and the question is asking the behavior, the probability that how this what is the probability that your value fit in the real life, the real situation. So because in this case they say that the call duration of WhatsApp call, whatever call they are doing, it is a capital X, and this call duration follows exponential distribution. That means okay, it's parameterized by the lambda rate parameter, and they're asking the probability that what is the chance that the call duration is greater than 6 minutes. So I think that it's very easy. You can just do
Yeah,
you have found this.
yeah.
Yes.
Maybe it is complementary of CDF.
Yeah.
That means
Yes.
e to the power lambda x. Maybe.
So how will you write it that you, because you want this probability x greater than 6 minutes, it will be uh, 1 minus
Minus both. One minus
probability that x is less than or equal to 6 minutes. Okay, so this is actually what this is actually nothing but CDF. Okay, which you call it as a CDF. So normally we do, I mean, just minus CDF 1 minus 2, so you can get the other part. So this is so you can see that this will be equals to 1 minus, and this is 1 minus e to power minus 1 by 3 into 6. Okay, so this will be 1 minus 1 plus e to power minus 2. So obviously then the here I think 0.135, the book shows 0.135. Okay, or like 13.5%. So this is the chance probability that a random variable x greater than 6 minutes. So such kind of problems are very common in case of exponential distribution, and they are very fairly easy. They are very easy, so nothing to worry about. There is a very important property of exponential distribution. Let me write it down clearly. It is called as let, the problem with this pen is that it becomes weak and weak. Memoryless memoryless property of exponential distribution. So I'm just write down the property. Probability that random variable capital X, which is exponential, is greater than s plus t, given that the random variable X is greater than s, is equals to probability that random variable X is greater than t. So this is called as memoryless property of uh, exponential distribution. And why it is called memoryless? So just read just write down the problem, and then you can see that probability, it is given that this event has happened. This part, probability that x is greater than a small s, because there are two values. One is s and t. So given that the random variable x, if we suppose that random variable x is a waiting time, someone is waiting for a bus. So given that someone has already waited for s time, so this is the time which has been done. Okay, so what is the probability that s plus t? Okay, so this is additional weight. Okay, so it is greater than it is equals to probability that x is greater than t. So in a kind of notation, or to understand this, there's a very simple example, that if someone is waiting at a bus stop, and he or she is waiting for a bus, and 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 then he or she has waited for 10 minutes. Okay, and then bus has not come. Okay, so the wait has been done for 10 minutes. Okay, but if I come at the bus stop, then what is the probability that the additional time it will take for the bus to come? So it says that it will not depend upon how much time my other colleague has already waited. You can see that in this case it is independent of s. So this is, and I think it's true, because if someone is waiting a bus stop, and then he or she has waited for 10 minutes, and then bus has not arrived. Okay, so so if another guy joins in, and then he also start waiting, so the additional time, this is t time, because s has been passed. Okay, this additional time, uh, um, so the probability will be the same. This probability, and for the coming of a bus, or for the coming of a packet on a link, it will be the same that for the year, because it does not depend upon how much you have waited previously. And just to make it more clear, that on a graphical line, if event is occurring here. Okay, so if you can at this point, you waited till s seconds. Okay, but the event, or whatever bus has not arrived, or whatever your event is, it has not arrived, and someone comes here again and started waiting uh, for t. So this is the t, and this is the s. So so the thing is that now the probability of this event occurring is only dependent on t. It is not dependent on x. So that's why this thing is not included in the probability, and therefore it is called as a memoryless property, and it's only the property of exponential distribution. I think it's also logical because that if the time which has passed, it has no impact on the. It is not controlling on the arrival of the event. For those who arrive late and start waiting for the event, it is the same probability. So this is called as a memoryless property of the exponential distribution. We have a kind of interesting numerical on this, so you will get it more. Okay, so let me illustrate the example. The example is this is regarding, they say that suppose that a switch has two parallel links to another switch. Let me try to make a diagram of what the author say here. This is example 35 of your book. If you want to read this, it is example 35 of your book. They say that suppose that a switch has two parallel links to another switch. This is switch 1, this is switch 2. Okay, they say that there are two parallel links between switch 1 and switch 2. Okay, consider a packet A that arrives when both links are in service. So a packet, this is the arrival link. Okay, so a packet A arrives here, and and both links are in service. Therefore packet will be sent on the first link that becomes free. So whatever link becomes free, the packet A will be sent there. If this link uh, is sent free, the first link, then it will be sent this side. If this link becomes free, then it will went to the bottom link. Okay, suppose this is link 1. So this is, let me write it down. This is link 1, this link 2. So the problem is that any a packet A arrives on a link, and there are two links between switches, switch 1 and switch 2, and whatever links becomes free, the packet A will be switched over there. So packet will be sent. They say that it's given that uh, what's the question? Just me read it again. That they say that a packet, when the packet A arrives, both links are busy. Therefore, the packet will be sent on the first link that becomes free. Suppose this is link 1. Now, assuming that the link service times are uh, exponentially distributed. Okay, so they say that the link service time are, the service time on a link is exponentially distributed on both links. Okay, and then this link 1 link, they also say that link 1 becomes free first. This link 1 becomes free first. Okay, uh, suppose that link 1 and because, so this will be switched to the, because it is becoming free first. Now distributed, which packet is likely to finish transmission first, packet A or link 1, or the packet should again reconsider the scenario. I repeat the scenario. There are two switches, and there are two parallel links working on them, and maybe due to HA, and then the packet A. At that time, both links are busy. It means that there is a packet in service at link 1, and there's also a packet in service at this link and also at this link. So A has to buffer. It will have to wait for time. And then it is given that link 1 is becomes free first, and also given that the link service times are exponentially distributed. Okay, so the packet this one becomes go say link is it is the packet already here, which is completing the service here. So the question is that um, which packet is likely to finish transmission first, packet A on link 1 or the packet already continuing service on link 2? The case packet on link 1 will go out first or the packet on the link 2 will go out first.
The
Yes, so what are your thoughts?
packet will pass through a link one because become free first.
There's already a packet at the link 2. The question is that uh, let me clarify the question again. uh, which packet is likely to finish transmission first? Packet A on the link 1. You're right that the link 1 becomes free first. Therefore, packet A goes to link 1. So it will not go to link 2. Okay. So the packet A will go to the link 1 because it becomes free first. It will not go to link 2. Link 2 has already a packet. Maybe due it has a larger size. It's continuing service. So so in the second time instant, packet A has arrived at link 1 and it is continuing service, and there's already the existing packet at link 2 is completing service. The question is that which packet is likely to finish the transmission first, packet A on link 1 or the packet continuing service on the link 2? So this is the question. So you need to think how can because this is the case, you are given that the link service times follows exponential distribution, so you can take advantage of two things. One thing is that memoryless property of exponential distribution, and I think that one of the important thing is that you should as a common sense you should know that packet can am I right to say that a packet service time is proportional uh, directly proportional to its size? If the packet is bigger size, it will take long time to process at an interface, and if a packet is of less size, it will take less time to process as an interface. Is it correct or not?
I
Yes,
think
it's
yes.
correct.
Yes, it is very logical. Okay, so if you see that uh, uh, due to memoryless property of exponential distribution, uh, at at the moment we cannot say any exactly that the expected remaining time on link 2, uh, because due to memoryless property it can be same. But if we are given if we because we don't know the service time for A, if a packet service time is proportional to its length, and we know that we know A's length, then we no longer have exponential service time. We know that it's precisely. And so the thing is that you cannot solve this numerical. I mean, it's the case that just to know that without knowing the exact this time, because you just need to show this, is it possible to solve or not? So uh, having such data, it's not possible to really conclude. You can say that due to memoryless property, both are likely. Okay, this is also likely, equally likely, and this is also equally likely. But the thing is that the one with the less size, and why we say likely, due to the this again this memoryless property, because this packet is already in service. Okay, and this is just joined now. So the point of departure, the probability of departure, it remains the same for both packets. So the answer is that um, the probability is same for the departure for the both packets or the both links, due to the memoryless property. This link is already in service. Okay, and this link has just arrived after waiting. But the thing is that this is also depend upon that the packet service time is proportional to packet size. So in this case, the if packet sorry if the packet A size is less, packet A on link 1 size is less sorry is less than the other packet is less than the other already in service packet at link 2. Okay, so if a packet or link 1 size is less than the other already in service packet at link 2, then due to memory less property then due to memory less property, what we can say that the the link 2 which is already in progress, it will not be impacted, and then it will depart first. Okay, due to memory less property, the packet A will depart or leave first only due to this. For any other distributions, we cannot say like this, but here we have just taken advantage of the exponential memoryless property of the exponential distribution. For other distributions, we do not follow memoryless property. We cannot say like this. So in this case, we have taken advantage of the memoryless property, which is this, like it is written here, that the time is just simply says that the one who has the time which has already been weighted has no impact on the new waiting time. So that's why we have used this property here, just to make sure that the both links are equally likely to default and will depart first. Okay, so I think this is clear to you. Okay, so now we come to, after exponential distribution, now we come to a very important distribution, which is called as Pareto distribution. And this is something very important, and it will take I think I need to restart this, sorry. So the fourth distribution is called as Pareto distribution, and let me summarize its notation. This density function is also called as a power law distribution, very common in case of internet traffic, and it is called as uh, alpha over beta, beta over x to power alpha plus 1 if x is greater than beta, and if x is less than beta, the density here is 0. Okay, so this is the uh, what we call as the formula for the density for the Pareto distribution, and its CDF probability, that random variable, let me write it more clear, is equals to probability x less than equals to x is equals to 1 minus beta over x की power alpha if x is greater than beta, and if x is less than beta, so this is 0. So you can see the role of beta here. The beta is very important, because any value of x, if it's less than beta, that Pareto random variable has a minimum value of beta. For any random variable, for any value less than beta, the density will be 0. So that's why some people say that the Pareto random variable, they say that their domain is beta comma infinity. This means that beta is the minimum value, this is the minimum value, and it can go. So this is the working domain of this random variable x if it follows Pareto model. So we will talk on more of this, how it works and how it behaves, and how come this happened here. Okay, so just to be to be more clear, I will try to make a derivation here, that let it to be uh, that the Pareto random variable. Okay, so we write it like this, is equals to due to power law nature, just any distribution which follows power law, v x की power minus u, and and x greater than w, and x less than w, it is 0. So this is the same thing we stated in a very simple manner, that this is the power law behavior. So this u is the main controller of the tail. This is the uh, tail controller. Okay, so this is the, and if you plot, so it just like looks like this, like this. So this is your w or beta, what is the minimum value. So this is the way. So and you know the property here, that all of the, as one of our friends mentioned is there, that if we do like this, area under the curve, entire curve, is it equals to, area under entire curve is equals to 1. Okay, so we can put the value here. uh, so this is the general fact, area under curve, a what we call area under entire PDF. It's a general fact, because it covers all of the probability values, so it's always area under the PDF is 1. Okay, so so here what we are doing, I'm just trying to derive the main because you might be asking that how come sorry, how come these values came into being. So I'm just starting with the normal standard behavior of any power law distribution. This is the standard behavior function x to the power minus u. This is standard formulation of any power law distribution. So I'm just trying to derive the Pareto behavior from this, and this standard formula, the power law formula is, it just says that 80% of the wealth is in the hands of 20% people. So this is just nothing in only said in a mathematical manner. So here, after having said this, I just applied the main fact that area under the density function is 1. Okay, so what I'm doing, that in this case, let it to be more clear, in this case, what is our lower range? Can anybody tell me what is the lower range? Can I split it like this, because we have two limits, uh, minus infinity to beta, okay, or what we call as the W here, fx dx, and plus, you just see it here, and plus w to infinity fx dx is equals to 1. So and you can see that for any value less than w, the probability is what? 0. So this part is minus infinity to w, the lower limit. This is 0 into dx plus w to infinity, and here the formula is uh, v x की power minus u is equals to 1. Okay, so this thing is gone here, and we are left with what? We are left with uh, w infinity v x minus u dx is equals to 1. So we can take the v out, v w to infinity x की power minus u is equals to 1. Okay, so how can we solve this basic integral? Anybody can remind me? This is the, I think, v uh, x की power
Minus u
minus u plus 1,
over
and
minus
yes,
u.
yes, is it okay?
Yeah.
And the limit is, lower limit is w, and the upper limit is infinity. Is it correct?
Yes, sir.
Is equals to 1. So what which we should make sure in order for this, because this, let me make it more clear, that it will be v over 1 minus u, okay, v over 1 minus u x की power minus u plus 1, and this is the limit w infinity is equals to 1. Okay, so uh, in order for this integral to finite, for this integral to finite to exist, or to exist, we must have, so I just want, it's a very basic question, that uh, that what should be the condition for the limits that this integral must exist. Otherwise, you see that the limits are the, because you see that the limits are the limits of this w, this is the minimum, this is the minimum value here. This is just like the beta in the previous notation. So the w is the minimum value, and the infinity is the maximum value of the random variable x. So this is the limit of x. So uh, we need to make sure that this integral remains finite. Okay, it does not go into infinity mode. So what should be the case? uh, I think to be more uh, precise, or make you understand, v over 1 minus u, let me put down the minutes and limits. First, you know the formula, what we do, upper limit minus lower limit, is it okay? So what is upper limit?
Upper limit infinity.
Infinity power minus u plus 1, and then minus again w
To the power
if,
minus u plus 1.
minus u plus 1. So we have just put the, so this is the whole thing is equals to 1. Okay, so so you see that this integral is still undefined, so we need to make sure that infinity things goes away. So what can we do so that this infinity thing goes away? What condition we must enforce What should be the condition so that we get rid of this condition, this infinity here? What's the condition? You can see that how to kill this infinity. Yes, please. How to kill this infinity?
So if we take this infinity part at the right side and under the heading of, I mean, 1 upon something, so it's 0.
Yes, you are right that we really need to do this 1 upon infinity. Okay, if this is 1 upon infinity, so then it will be 0 and it will be gone. So you do not need to wait for going to right side or left side. You just tell me that what condition I must enforce so that this infinity becomes 1 over infinity. You can see that. Okay, tell me one thing. In what is the power of infinity?
Minus u plus 1.
Sir, we can take
Minus.
common from the power.
No, cannot take common.
माइनस कॉमन ले लेना.
No, there's no. If I you see that you're not understanding my question. I'm saying you are trying to do some hardcore mathematics. I'm
Sir,
trying to avoid this. I'm trying.
sir,
Tell me condition which will make this infinity finish, make it 0.
if
What is the
I
condition?
make it 1 over infinity, if I
Yes,
make
one. So okay, let me tell. If this is infinity ki power, if there is infinity ki power positive, so
sir, maybe
what is the answer?
mm, infinity minus u.
Sir, if the power is positive, the answer will always be infinity.
Infinity.
If it's negative, it will go
It
down
will
to
be.
the
It will be okay. Yes. You are
so
right.
zero.
Then it will be 0. So tell me, how can I? What condition should I enforce that the power of this infinity remains negative? What condition? Now you now you can tell me the answer. You are very close now. What condition should I impose? Okay, what condition on the value of u should I enforce that it
Sir,
becomes
taking positive value of u
okay? Yes, you are right. You must say that
and
you should be greater
greater
than 1.
than 1.
Okay, so u must be greater than 1 for this integral to finite. Okay, and then obviously the w and w will be greater than 0. That's okay, but the main thing is that w is greater than 0. That's okay, but the main thing is that u, if we must ensure that u is greater than 1, then what will happen? If the u is greater than 1, then minus u plus 1. So you mean that if u is greater than 1, then it means that this thing which, or let me this red part, if I put a condition that u is greater than 1, so then this red part will always be
There is minus u
Sir,
plus
negative will always be
it will
negative.
always be negative. Okay, so what I'm doing now, that uh, that in order for this integral to fund exist, we must enforce the condition that u is greater than 1. Okay, in this case, then v over 1 minus u, then this will become 1 over infinity. Okay, and then minus w minus u plus 1 is equals to 1. So in this case, now we can proceed on. V over 1 minus u, this thing will be 0, and then minus w u ki power 1 is equals to 1. And then further we can simplify down. What if I write it here like I need to make it a bit more simple. Mm, uh, this is v. Can I make it like v over u minus 1 w minus u plus 1 is equals to 1? Is it okay?
Yes,
Is it
yes,
sir.
okay?
Yes.
Yes.
and then what I do is that I need to make v separate. uh, v is equals to, I take it on the other side, uh, v into w minus u plus 1 is equals to u minus 1. Is it okay now?
Yes,
Yes, sir.
sir.
Okay, now if I take it, v is equals to u minus 1 and then w uh, u minus 1. Is it okay?
Yes, sir.
Yes, sir.
So this is what we did. We find down an elaborate value of this v. So what I will do, I'm going to put down this value v back to where the original standard notation here. This I started from here. If you see it here, so this is, I wanted to put it over there. Okay, so if I put it over there, so I forgot. So let me write it down here for you to understand. So this f of x is equals to, what was v? It was u minus 1. It was u minus 1. I think I need to, I don't have the full derivation. What was the
Value u minus 1.
w power u minus 1? Uh, w power u minus 1. So this is entire v here. Okay, and then uh, x ki power minus u. So this is the case here. So we need to bit, so this I did nothing, I just put it the value of the v in this way here, and the other thing, so this is just the v here. So just need to bit summarize here. So I need to make it a bit simple. I just need to take the powers on one side. Can I do something like this? U minus 1 and then W power U and then W power minus 1. Is it okay?
Yes, sir.
I just break U minus 1 thing into two parts and then X ki power minus U, and then what I did, U minus 1, sorry, this is U minus 1, and then this is upon W, I took it here, and then W ki power U and X ki power minus U, and then I think I can summarize it more like U minus 1 over W, and then I think W over X ki power U. Is it okay?
Yes, sir.
Now, and so this is our density function. So this is the density function of the Pareto random variable. But in order to make it more clear, let me do like this. Let u minus 1 is equals to, because you know that u parameter controls the tail decay, but I am now summarizing it as a constant value, call it as a alpha. Okay, and this w is the minimum value, and then I just take w is equals to beta, which is the minimum value. So we are just changing the notations just to convert back to the standard form of the uh, Pareto random variable. But still, if you insist, this is again our final answer. This is the density function of a Pareto random variable. But again, we want to do like this. So just help me to finally summarize here. So, so if we do like this, u minus 1 is equals to alpha, okay, and beta, and then w upon x, and then what will be u? It will be just u will be equals to
alpha plus
alpha
1.
plus alpha plus 1. It will be equals to alpha plus 1. So alpha over beta, and then obviously, sorry, yeah, this is not, this is beta over x alpha plus 1. So this is now the density function of the Pareto random variable. So can we now prove it here? I think just go back here. Is it the same here? Just I hope you can see this. Is it the same thing which we derived? Is it okay or not?
Yes,
Is
sir.
it the same thing?
Yes, sir. Same.
So I think I would like to just those of you who could not understand what I did, it's very simple exercise. I did nothing to worry about. Just to make you understand, I am just here at the start of the lecture. I just write down the formulation of the Pareto distribution, which is a kind of heavy tail distribution, which also called as a power law. Here I just showed that the minimum value is W, and then it behaves. The tail decay is very slow. It's very slow tail decay. So it means that the chances of high values are not negligible. You must remember carefully that in all of the distributions which we studied till now, the chances of very large values are, or the chances of extreme values are negligible. But only in the case of the Pareto random variable, the chances of an extreme event, the chances of a rare event is very high. So that's why it used to model. Okay, and that's why we call it as a power law, or we call it as a power tail distribution, because the tail has power. The tail power means that tail is not decaying very slowly like Gaussian or exponential distribution, in which such kind of ordinary distributions like Gaussian or exponential distribution, they have always their values looming around the mean value and the variance. But it's not the case in case of Pareto distribution. We will study more on this, but here I just wanted to present to you a mathematical formulation, how we derive the distribution. So after writing this formula, after writing this formula, I just don't want to, because the formula is a bit complicated. So I wanted to show you how I actually derive this formula. Okay, so I just started with the notion of a power. What is a power law function? X ki power minus u. This is x ki power minus a, or x ki power. This is a power law random variable. This is because this, it is decaying and the tail power is controlled by a. Um, uh, the less the value of a, the slower the function x will decay. The higher the value of small a, the faster it will decay. You all know this basic mathematics. Okay, so I just took a general form. V is just a multiplying variable. It can be 1, it can be any value. It's a constant value. So V is a constant value, and x ki power minus u, and u is again a constant value. But the difference between V and u is that V is just a constant value. It has no role in the distribution, but the u is controlling the tail decay. That's why I call it as a tail controller. And then obviously any value less than W, I then define the range, that this is valid in this range, and if this less than W, okay, this is W here, then it will be 0. Then what I did, so this is the general formula of any power law distribution. And then what I did, I just applied the basic stats, that any density function, the area under that density function is always 0. The area under the full density function is always 0. So that's why I started from this basic property, and then I just feed it here, the about the fx, I just feed it here. And then you can see that we have two limits, because the values for of random variable less than W, the probability is 0, and the for values greater than W, we have this behavior. the power law behavior for values greater than W, because for value less than W there's no power law behavior, there's no distribution, all the chances are zero. Okay, so then I did nothing. I just break the limit into two parts, minus infinity to W and then W to infinity. And obviously you all know that for this part is zero because there is no probability mass in here. Okay, and then this part is behaving as a power law. Okay, so then I just put down these values here, and then I put the v, the x power minus u, and then I just solve it like this, and then I just try to find out the value of v here, because my objective was here just to find out the value of the v here, so that you can get the clear idea of the distribution function. So while finding the value of v here, I faced a problem. The problem is that when I applied the limits, the integral became infinite. It was not able to exist. Then I did not stop. I just made sure a condition. I just applied a condition. Okay, if u is greater than one, then obviously this part here will always be, the power will be negative. Then it will be always be 1 over infinity. So that's why 1 over infinity will be 0. So that's why I was able to get rid of this infinity, and then this way I found the optimal value of v, and then I just did nothing. I go back here, and then I just put this thing, you can see. Then I just put the value of v here in the basic notation of the density function of any power law random variable. I put the value of v here, and then I just solved it down, and then I got this here. And then finally I just simply u minus 1 is equals to alpha, and then w is equals to beta. This just basic notational difference, and I found that this alpha over beta, beta over x power alpha plus 1. So this is the main, what we call as the famous probability density function of uh, Pareto random variable. And here what is beta? Beta is the minimum value. So for any value less than beta, the density function will be equals to 0, and this all behavior appears for random variables which are greater than the minimum value, greater than the beta. And you can see here that the random variable is capital X, the values are small x, and then which parameter is controlling the tail? It's previously it was u, now it is. Yes, please. What parameter is controlling the tail? It is alpha. Alpha is the tail controller. Tail controller. So I just try to make it very simple, that now this is the main formula for the density function of the Pareto random variable. And just as a to tell you, one of my PhD student is doing is focused on alpha, and we have very different estimators of alpha for a Pareto distribution. It's not not in your domain to study, but one of my PhD students is doing work on the sequential real-time estimation of the heavy tail index, because this alpha is also called as a heavy tail index. And this is it looks something trivial to you, but it's not easy to estimate from the real data. And just to tell you that in 2017 or 18 I got almost 8 million rupees grant for this project from HEC. So the project is still continuing on, so the half is complete, but still this part is I'm working on for developing the sequential estimators for heavy tail index alpha. So but nothing to worry about. It's just the work I'm telling you about my what I do. But for you it's only to understand is that alpha is the heavy tail index. It's control the tail of the Pareto distribution. So I hope the derivation is not problematic to you. It's very easy. And you may ask how to do this. You can you now derive this thing, because you have done this, but how to do this? Yes, please. You have found a density function. So how to find the CDF? This is called as CDF. I think you should do this. Let me give you a hint. Let me give you a hint. You can do it. Uh, Probability random variable x is less than equals to x. It's always minus infinity to plus infinity. The density function. Okay, so in this case, our limit is the lower limit is beta. Okay, so you just need to put like this, beta to infinity, and then what is fx? This is alpha over beta, beta over x to power alpha plus 1 and dx. Okay, so can anybody help me solve this? Take all the constant values out and then you can solve it. Yes, please. This is basic inter-level maths. Can anybody tell me the answer? Let me try to solve all the constant values independent of x. I will have to take out. This is alpha over beta. Okay. Then beta over x. I think I need to be more clear.
Sir, we should extract p to the power alpha plus 1 distribute.
This, you mean this?
Yeah.
Yes, sir.
Alpha plus 1 dx. I think we can further take this out or not.
Yes, sir. Sure.
Alpha beta, what I take out?
Beta to the power alpha plus 1.
Power alpha plus
So what I got?
1 over
Integral
x.
1 over x alpha plus 1. How to solve this? Okay, and then I think this we can do this. This beta and this one cancel. I think we go. Is it okay? This will be alpha beta.
yes, sir.
Is it okay?
To the power
And
alpha.
yes. Thanks for correcting this. Moona is very active. Otherwise, you know that if you do any mistake, this goes very problem. Thank you for telling me this. So can I write Moona like this? This one is beta x ki power minus alpha minus 1.
Plus, yeah.
Yes, sir.
Yes. Is it okay?
Yes, sir.
Let me further try. Actually, I can just try. I don't have this. My luck here. So how to do this? Solve. It's very simple integral. I think the same thing.
Yeah, alpha x to the power.
X ki power minus. Now we need to minus alpha minus 1 plus 1.
Yeah.
Okay. And
Minus alpha
minus alpha minus 1
plus 1.
plus 1. And then limits are.
Beta to infinity.
Okay. So now the situation turns out to be alpha beta ki power alpha, and then this cancel, this cancel, this is x ki power minus alpha, and then sorry, this is minus 1, and this is what? This is minus alpha. So what we should do now?
You can extract minus alpha from the limit.
I think yes. So this will be equals to, I think this will cancel. Yes. This will be minus beta
Yes,
power
sir.
alpha. Yes. Okay. And then what we are left? X ki power minus alpha, and then
Infinity.
beta or infinity? Which are the limits of which are the limits of x? Sorry, I should not write it as a bracket. It is x ki power minus alpha, and upper limit is infinity and lower limit is beta. So we are now left with nothing other than to open the limit and see what happens. Minus beta ki power alpha, then these are the limits of x, so therefore we will put limits in place of x. uh, alpha ki power alpha power minus alpha minus beta uh, alpha power minus alpha
Alpha.
minus beta ki power alpha. So this is so how to get rid of this infinity here?
The same, sir. The same in the question in the derivation, the first derivation. 1/2 to the power alpha
Mhm.
equal to 0.
I think we need to do something here. Hmm. X ki power, this was what? Minus alpha?
Sir,
Yes,
yes, sir, now it's right. That was
minus.
my.
Is it okay now?
Yes, sir, it's
Yes.
okay.
Hmm. Um, we need to wait for a while mm, uh, because in case of what we will do in this case, you know that this alpha is what we call it as a maximum limit. Okay, so what we do, uh, we take it, although you might not agree with me, but let me try that. This is just allow me for a while, in place of, although the upper limit is infinity, but I am putting it here as x, although it will maximum, it will be infinity, but at the moment I am trying to put it as a x. Okay, so you will understand very soon why I behave like this. Okay, so the maximum value of x is what? Infinity, because you know that this is the upper limit. Okay, so but wait for a moment and then allow me to go like this. So this is, so can I just go inside now? This is minus beta x ki power minus alpha and alpha, and then plus this minus into minus plus, this
Beta,
will be beta alpha and then
beta minus
beta.
alpha.
Okay, so this, I think this whole thing will be uh,
Yes,
0. 1 1.
0. This will be beta ki power 0, and will be,
yes.
and what about this side? How can we do that like this? Can we do like this? Beta over x
Alpha.
Beta
alpha
alpha. Yeah.
minus, okay, and this thing will be equals to uh, beta over x alpha plus 1,
Plus 1.
or now we can add like 1 minus beta over x alpha. So what we finally got? We finally got the probability
This
that the Pareto random variable x is less than any given value small x. So can we match it with this? Is it okay now?
yes,
Go
sir.
back.
But why you put x
This
rather
this this
instead of
is, yes. So so now the question is that uh, why we did like this. Coming back to this, because uh, the upper limit was
Infinity.
infinity here. So this is the thing which we need to understand, that Wherever the case, I think this is the point. So this is the point of controversy. This point. So this location, I did a trick because instead of putting infinity, I put the value of x as a limit of x. Okay, so this is sometimes although this behavior will go to infinity. Okay, so we say that x will maximum value of x will go infinity. So in this case, uh, what will happen if I put back infinity here? What will happen if I put back infinity here? Because then I think you may agree
Sir, it will become zero. This part will become zero.
this part will become 0, and then 1 minus 0 will be
One.
1. So in this case, that mm, probability that x is less than infinity is equals to
One.
One.
1. So that's a particular behavior of that heavy tail distribution, that for such cases the data, even if the data is too high, so that's actually the beauty of this distribution, that we need to deal with these infinity values and then how to model them. So the thing is that we just hide the infinity is still there. Infinity is still there. I have not changed the behavior. I just kept the value of x, and the limit is underlying this derivation, so you can put it back anytime. Okay, so but this is the thing is that we just got as a decent form of the ccdf. Okay, is it clear now?
Yes, sir.
And now it's I give you some very easy task. The tasks are to find and I hope you don't kick me out. The tasks are mean value, mean and variance of Pareto random variable. I just you give you a hint because you're very tired. We will just finish the class, and then I just give you a hint. The mean value of random variable x is any random, and the mean value of any random variable is minus infinity to plus infinity x times fx dx. Okay, so this is the mean value. What will you do? You will take the x as it is, and in place of fx, you will put what? You will put
PDF.
this thing. You will put this thing. Okay, so you will find the mean value. Let And during this mean value, you will face the problem of the limits also. I'm telling you. Okay, so this is the mean value, and for the variance, for variance of x, for variance of x, again it's simple. You need to do I can tell you the formula here, then you can try to find out the variance. The variance of random variable is e of x square minus
X whole square.
this square. So for this, you may need to repeat some calculations. So this, again, don't. So I will do this here for you, but I want that it might be a bit, because this derivation looks a bit easy, but it's long. So what I want you to do, just very simple, just do this and do this and find out the formula. And I can tell you for your convenience, I can tell you the answer for the mean value should come out to be alpha beta over alpha minus 1. And for variance, I let me tell you, and for variance it should come out to be I think this part can be written like this: alpha beta over alpha minus 1 square. Okay, and then this is alpha beta square over alpha minus 2. So this is actually this part, and this is actually this part. This is just a square of mean value. So don't worry about this. Just take some heart, and you can do it very easily, and then you will face the problem of the integral becoming infinite. Just take my advice. Just take my advice. Whenever an integral becomes infinite, then just try to find conditions for which the integral becomes infinite or becomes zero. Okay, so you will do this. So I'm not going to derive this now in this class. I'm just giving you an assignment. Just try it. Just try it. It's just a simple a metric or interlevel mathematics, but you just need to be careful, and then you will really see. And during this derivation, you will also understand what is the meaning of infinite mean and infinite variance. Okay, so I'm not going to go further for this class because it might be a bit heavy at this moment. I will help you derive this in the next class, but I will try. It's my wish that you try to find out the mean values like this. I have written to the formula, and meanwhile you will also see what is mean by the infinite mean and infinite variance. Okay, so this is the thing I you will learn by this derivation. So actually till now what we have done was not a big deal. This is now a big deal. This derivation, the derivation of the mean value of a Pareto distribution, and the derivation of the variance. This is the important thing which I need you to understand. All these things which I derived for you is just uh, for you to understand. Is nothing very important. In examination, this kind of thing may not come, derivation of a density function, but this thing, finding the mean value and the variance of a random variable or any given density function, this is also important for your examination. Okay, so I hope you will try it, and then we can discuss it in the next class. Okay.
Inshallah.
Okay.
Yes, sir.
Okay, thank you very much. So I finished the class here now, and the midterm, I haven't graded the midterm marks, but I will try best that before the next class we will do it. And I might request you, because we are short of 1 or 2 classes, so maybe a short class we might need 1 or 2 hour class, or maybe Saturday or Sunday. Is afternoon time is okay, like 2 to 5 or 3 to 5?
Yes,
Sir, in
sir.
coming, sir, in
Sir,
coming
So
Saturday.
Saturday, Sunday, we have a midterm of 2
Uh,
subjects.
on
Yes, sir.
Saturday you have a midterm. On
In
Sunday.
Saturday, Sunday, both on both days, we have a midterm.
So what Elahi Baksh tells me that this class has no clash on Monday. So can we do a extra class on Monday? Like I think nobody of you has a class on Monday.
सर मंडे को भी हमारी क्लास होती है
On Monday as well.
यस सर
Yes, sir.
Okay, let me ask Elahi Baksh. So okay, meanwhile you try this, and then we meet next week. Okay. Okay.
ओके सर
Okay. 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 Thank you. Thank you. Thanks. Stop. I will share the recording. Okay.
यस सर थैंक यू
So I am here for a while for questions, and otherwise you can leave the class.
हाँ सर
Hello.
सर ये थिंक टाइम जो यूजर थिंक टाइम है बेसिकली ट्रैफिक काउंट मॉडल में हमने इस्तेमाल किया था पेरेटो डिस्ट्रीब्यूशन और उसमें टेल इंडेक्स की जो वैल्यू है वो 1 से लेके 2 तक रखी गई थी और इंटर अराइवल पैकेट को जो है वो लेस देन 1 की टेल इंडेक्स दी गई थी पेरेटो डिस्ट्रीब्यूशन के अंदर तो उस पर मैं
अच्छा आपने टेल इंडेक्स की रखी डेरिवेशन 1 to 2. इट मींस दैट finite mean and infinite variance, because
जी बिल्कुल
टेल इंडेक्स ये अरे यार ये याद कराते ना, आपने याद क्यों नहीं कराया? क्योंकि जो हमने डेरिवेशन की है इसमें ये तो है, टेल इंडेक्स में it's about alpha bit चलेगा ये. This thing I will actually prove next class में I will prove actually कि alpha between 0 and 1 both mean and variance are infinite, and alpha between 1 and 2 mean is finite and variance is infinite. So yeah, I will prove in the next class. but for internet traffic and other think time data, it's very common trend in research articles that they take the value of alpha between 1 and 2. So you did right.
अच्छा सर, दूसरा ये कि ऊपर जो आपने ये अभी न्यूमेरिकल करवाया था, इसमें
It's just
एक्सपोनेंशियल,
derivation. Numerical तो नहीं, just a derivation थी ये भी तो.
नहीं सर, ऊपर जो आपने जो न्यूमेरिकल करवाया था ना, जिसमें एक्सपोनेंशियल डिस्ट्रीब्यूशन की बात कर रहा हूँ सर मैं,
अच्छा वो
जिसपे
that case. Okay. स्विच वाला.
जिसपे आपने जो पीडीएफ कैलकुलेट करवा था, आई थिंक प्रोबेबिलिटी ग्रेटर देन 6 का जो किया था, तो उसमें मैं ये पूछना चाह रहा था कि कर्व जो प्लॉटिंग होती है बेसिकली उसमें, तो वो कर्व जो है वो एसिम्प्टोटिक होगा और राइट स्क्यूड होगा, जो शेडेड रीजन है, एरिया अंडर द कर्व, उस पर्टिकुलर न्यूमेरिकल की बात कर रहा हूँ मैं सर, जो आपने करवाया।
जी जी, मैं समझ गया। उसमें हमने ये किया है ना कि हमने CDF लिया. CDF is giving you the left skew. Everybody knows that the CDF, the answer of CDF gives you the left skew, and that's about the values of x less than a given value. और उसका राइट स्क्यू मालूम करने के लिए हमने क्या किया, 1 माइनस CDF कर दिया.
तो उस केस
तो
पे राइट
पूरी
स्क्यू,
हमने लेफ्ट.
इस
जी जी,
पर्टिकुलर
तो
केस
राइट
में
स्क्यू
राइट
मालूम
स्क्यू,
करने की. हम्म.
तो मैं पूछ रहा हूँ कि आपने
आवाज
जो
आवाज कट रही है आपकी.
सर
जी
मैं
जी, आप
पूछ रहा था
बोले.
कि जो न्यूमेरिकल जो सॉल्यूशन था, अगर हम उसकी प्लॉटिंग करें तो वो राइट
हम्म.
स्क्यूड बनेगा ना?
बिल्कुल बिल्कुल, वो सारा लेफ्ट का पूरा पार्ट जो है ना वो कट जाएगा.
बिल्कुल, ठीक है, यही
वो राइट वाला
कंफर्मेशन
सा
करना था।
पार्ट, वही सारा राइट का पार्ट आ जाएगा. तो उसको आप मतलब इन द टर्म्स ऑफ स्क्यू ना बोलें, क्योंकि स्क्यू का लफ्ज जो है ना वो थोड़ा कंफ्यूजिंग है. दैट्स समथिंग एल्स. आप उसको वो बोलें बस. पूरा PDF का हमने एक पार्ट, लेफ्ट पार्ट हटा दिया, राइट पार्ट हमने ले लिया. वो स्क्यू से ना वो थोड़ा वो आपको पता है, स्क्यू कट, स्क्यूनेस, कर्टोसिस, ये अलग अलग टर्मिनोलॉजीज हैं.
ठीक है।
इसमें आप लोग वो ट्राई करते हैं. मैं कहना बार बार भूल जाता हूँ. ये जो न्यूमेरिकल्स में करा रहा हूँ, बुक के जो आपके एग्जाम्पल प्रॉब्लम्स है वो ट्राई करते हैं आप लोग. वो ट्राई करें ना. कोई मतलब इट्स फॉर प्रैक्टिस. आपकी जो
बिल्कुल
बुक है
सर,
जो मैंने शेयर की हुई, इसमें ना जो प्रॉब्लम्स मैं करा रहा हूँ उसमें इसके वो भी मैं कराऊंगा बाद में, सारे प्रैक्टिस में सॉल्व भी करवा दूंगा. लेकिन ये कि आप लोग ट्राई तो करो. ये जो जितने प्रॉब्लम्स हैं, अभी मैंने एक चीज मैंने स्किप कर दी है ड्यू टू कंटिन्यूटी. ये इनइक्वालिटीज, क्योंकि अभी अभी हमने पढ़ी डिस्क्रीट डिस्ट्रीब्यूशन, देन वी स्टडीड कंटिन्यूस डिस्ट्रीब्यूशन, फिर हम उस पर आ गए इनफाइनाइट वेरिएंस डिस्ट्रीब्यूशन आ गए. लेकिन हमने एक पार्ट में स्किप कर दिया इनइक्वालिटीज पर मैं. तो अभी ये खत्म कर लूँ तो मैं उस पर मैं आऊंगा, इनइक्वालिटीज पर. तो उसमें भी काफी न्यूमेरिकल्स है आपकी बुक के अंदर, काफी इंटरेस्टिंग न्यूमेरिकल्स हैं जो कि पैकेट ट्रैफिक में काम आते हैं. ठीक है. ओके, सो थैंक यू वेरी मच फॉर योर टाइम. सो बट यू नीड टू ट्राई. जो दो एग्जांपल दिए ना मैंने, यू ऑल नीड टू ट्राई, सो दैट फिर आपको पता लगेगा कि व्हाट इज मीन बाय द एक्चुअली द इनफाइनाइट वेरिएंस डिस्ट्रीब्यूशन. ओके, so thank you very much for your time. I'm again here for a while, or you can leave the class. Okay, thank you.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
थैंक यू सर।
Thank you, sir.
थैंक यू सर।
थैंक यू सर, अल्लाह हाफिज।